Alrighty. So, let's see here. This is my very first time booting up Last Call BBS. So, I'm hopping into this blind for some background. Last Call BBS is Zach Barth as Zachtronics, his last game under the Zachtronics brand. And it is supposedly kind of like a collection of all sorts of games that he's made that didn't quite, well, I guess like every single game wasn't like big enough to be its own commercial release, so they just kind of got conglomerated into Last Call BBS. And one of these games is supposed to be a thing called ChipWizard, ChipWizard Professional. For those who don't know the history of this game, one of the very early Flash games that Zachtronics released, well, more like Zach Barth made, is a game called Constructor, which is spelt like K-O-H something, like Kohctr, or is that right? Anyway, it's supposed to be written in Cyrillic, and I can never remember how it's actually written, because it's like Koki Pike Top whatever something, and yeah. So that game there was a flash game of um, like a silicon, like an integrated circuit kind of simulator kind of thing. Hello, Rolomni, and welcome to the stream. So, this is, okay, what is this? Handymate. Ask and you shall receive. This is my old Sawayama machine, all set up like it was back then. I even got the BBS running again, so you can dial in and download more of these retro games. I have to admit, I'm still getting used to that term. Anyway, the story of all this stuff is also a story about people, so I wrote a few notes about how I came across these things and whatever else came to mind as I was getting it ready. You might find it interesting, you might not. It's there either way. Have fun. What do these things do? Oh. Okay. Ah. I was like, there's no what's a taskbar down here? I'm just okay. So there's system, there's solitaire, there's this thing, there's drive zero. Oh man, those are some very interesting sounds. Full screen versus windowed. I think I'm gonna go full screen. Ooh. Wait. Okay, that means that my this window, this is a 1440p monitor that I'm playing this on, so everything's kind of really zoomed in. Ooh. Ooh. Yeah, I guess I'll stretch it. Screen effect. Oh, that's cool. So yeah, that is emulation of like a CRT because it's got these weird rounded edges at the bottom. Um, just a complete side note, one of my personal projects is I'm taking apart a CRT monitor so I can try to turn it into a vector scope. And yeah, these things are ancient. CRT production peaked in 2000 and it's been downhill ever since then, so. Okay, sound input. I actually used Dvorak, so there's a screen reader? Okay. I will not be using that. Histograms. Leaderboards. I'm gonna hide the leaderboards. Nah, it'll be fine. I'll show the leaderboards. Top percentile, 10th percentile, sure. Cool. So, Netronics Connect. Okay. What is all of this? Dial last call BVS. Oh my goodness. Oh my goodness. Wow. I cannot believe that you actually parodied the dial-up tones. Okay. Oh boy. Whew. Okay. I started the BBS thinking nobody would really use it, so imagine my surprise when the first user dialed in, then the next, then the next. I like to think it was a big community success story, although you can't argue with the free downloads either. People used to call that wares, and the computer industry called it illegal piracy. I won't try to justify it, I just wanted to share the cool stuff I found, and a lot of which you couldn't get any other way. For a while, Last Call was about as big a BBS as you could find in the Kansas City area. That was important in the era of long-distance telephone fees. Interesting. Okay, press a key to find more information. Can I click? No, I actually have to press a key. Okay. Yeah. Thanks for allowing me. Yeah, it really has to do with, yeah, I'm a electrical engineer, or my undergrad was actually material science, but I got really interested into electrical engineering towards the end of my material science undergrad. So I kind of really did a lot of self-study. It was kind of like a hobby for me as well. And I ended up doing electrical engineering as my master's degree. So there's a lot of these funny little things that I'm like, wait a second, I recognize this from like ancient electrical engineering technology stuff, which is always fun. Something different from our usual fare. This download is a professional computer-aided design program for integrated circuits. You ask, Barkeep, why the heck is this on here? I say, why not? More to the point, this software package normally costs thousands of dollars. So go ahead, give it a spin and see what the big boys do with their machines. No software protection dongle required. Okay, yeah. Zach definitely did his homework here. In a real chip design industry, we use a program called the big one that a lot of people use is Cadence Virtuoso. And Cadence is the name of the company that makes it. Virtuoso is the actual name of the program. That, if I recall correctly, it's something like they charge you for like every 6 seconds that you use it for in some cases, which is just insane. And if you want to get like an annual license, it's literally like tens of thousands of dollars. It is ridiculous. And the software is also really old. It's like something made in like the 1990s, I think. And yeah, it's kind of clunky to use, but it's kind of like, well, I was gonna compare it to another program, which is Altium Designer, which is for printed circuit board layout. It's kind of like, it's old, but because it kind of got its foot in the door really early, it's just become like the industry standard, so everybody uses it. And it's got, its quirks and features that you kind of have to learn to use because it's kind of weird like that. So yeah, that's the in the real world analog of this. But yes, download file is D. Okay. Is it actually gonna make me sit and wait for 2 minutes and 30? Oh my god. Well, I guess I should have done this before yammering my mouth off about chip design and whatever. Um, but yes, I guess I could talk a little bit more about chip design. So, what I actually do for my master's degree is so I took a class in analog integrated circuit design. Um, Unless I play solitaire, does it like speed up the download or something? Nah. Oh well. So, yeah, I first took a class in analog integrated circuit design in my first year of my master's degree program. And that's when I kind of like knew like yes, that is what I want to do for sure. Um, so I got in contact with the professor who teaches that, who is Dr. Hassler at Georgia Tech, and now I work with her in her lab doing research on field programmable analog arrays. Yeah. So they're kind of like FPGAs, but instead of, being digital, which is what FPGAs are for, it's got analog stuff in there as well. So you get to play around with all sorts of interesting circuits. Yeah. She also does a lot of research into things like what is it? Like neural networks. Um, she was really big into the neural network and neural computing craze in back in the 1990s. There was a kind of like a neural network thing going on back in the 1990s that kind of died out, and then the more recent one where everyone's like, oh, machine learning and AI, that kind of started more around like 2016 ish. So yeah, there's been kind of two big waves of AI and stuff, and she was part of the first wave, and there wasn't very much interest. Like the interest kind of died out, and then ooh, yeah, and it's kind of got revived a little bit later. So yeah, that's what several people in my lab slash Dr. Hassler's lab are working on. I think they're working on things like analog synthesis, neural network computing using neural networks. I think one student is working on like the hot field problem on like hot field networks. Um, yeah, lots of interesting stuff. All right, let's enough talking and oh man, okay. Very interesting. Right, that's the wrong one. Drive Zero. ChipWizard Professional. Okay, so I'm coming into this blind. View manual. Okay, interface, design elements, using capacitors, using transistors. Okay, let's take a look at that a little bit later. What is this? License key detected. Cool. What is this? This is March 13th, 1995. Actually, that kind of brings up an interesting question. I know Last Call BBS is kind of like this, like, retro futuristic thing, which begs the question, like, in this alternate timeline universe of, this stuff, where does, everything fit in this Actronics universe? But that's not something that I can really something that I'm not very knowledgeable on. Okay, Constructor Labs. So that is a reference to the Flash game Constructor. All right, let's now take a look at the manual, the interface, layout window, spec window, yep, simulator window, visualizer window. Okay. Design elements. So there's the silicon layer. Yep. Okay. Vias. Vias are small vertical wires that connect the silicon layer to the metal layer. Okay. With a via in place, signals will flow freely between the two layers. Okay. Yes, so a via in the real world again is actually actually you've got what we call are actually contacts and interconnects. Or you could also say via, but there's a little bit of an interesting difference because if you're not careful, because of a bunch of physics reasons that I'm not going to go into, if you just put like a metal directly on a semiconductor, you might accidentally create like a weird barrier there. So you have to mess around. Like the metals that you actually use to put directly onto the silicon is actually slightly different than the metals that you use to connect like one metal layer to the next metal layer. So that's why we say like there's a contact between the silicon and metal, and then interconnects between metal 1, metal 2, metal 3, on and on and on. But you can use via as kind of like a placeholder, everything. Okay, so there's this. There's the metal layer. Yep. And capacitors can be delayed by one or more cycles instead of flowing instantly. That is an interesting take on a capacitor. We'll get back to that. Creating NPN. Okay, creating PNP. Yep, using NPN, using PNP. Okay. You creating capacitors, charging capacitors, discharging capacitors. Okay, yeah. That's some very interesting interpretations of what a capacitor is. Anyway, so signal crossover. Okay, so it looks like I only have one metal layer? Really? Okay. Oh, so I can click to fast forward. Okay, so out A, in A. So it wants me to do something like, there we go. Something like this. Yeah, okay. And then out B is all the way over there. And because I only have one metal layer, I can't actually route over there. Okay. So, let's see here. So I need to, use a via, and, I guess I have to do this first, right? Let's get rid of this metal. Move it over here. Yeah, this is, not, because, I'm a little bit peeved at this. Let's put the via right, here. Let's erase all this. Get this metal going this way. Yeah. So a couple of things. Number one, usually you wouldn't do this in real chip design. That is to say, use the silicon layer to do this. Usually you would just go up to the next metal layer, but unfortunately we only have one metal layer. So the reason why we do that is because silicon is much, much less conductive than metal. I'm guessing it should conduct. Yeah. So yeah, the conductivity of silicon is pretty bad compared to metal. Even if you dope it a lot, you can only dope it so much and increase its conductivity so much before the amount of excess dopants that you put into the silicon starts to interfere with all of the electrons moving around. So like the electrons just kind of start crashing into each other, into the dopants themselves, and it gets scattered. So your resistivity, it'll go up because you're introducing more, dopant atoms and whatnot, and then it'll go down again. So anyway, But yes, metal is much better of a conductor than silicon. Uh, Engineering curious. I told you I got started in sales at Sawayama and also spent some time in marketing. I didn't enjoy my work, but after a while I wanted to try out something new. I've always been a tinkerer of sorts, and the idea of working on the engineering side was starting to appeal to me. Instead of only selling the machines, I could contribute to their design. Now that's something that I can definitely resonate with. I mostly switched over to design because I found out I did not want to be stuck in the clean room all day. Yeah, if you're a material science engineer, you kind of get pushed into the processing side of circuit making like chips into making integrated chips. You actually need to, if you want to get into design, you need to do something more like what is it called? Yeah, you actually have to go into electrical engineering and do that. All right. Problem was, I really had no idea where to start. Luckily, during my time in Japan, I made another friend who worked in engineering at a small firm that was owned by Sawayama. His name was Daisuke Don Iwashiro. Sorry, I'm not Japanese. I tried my best. Oh, it's all the way down here. Oh, interesting. Whoops, probably shouldn't have closed that. I'll bring it back up. Just minimize that. And okay. So yeah, another thing is you probably wouldn't route these two lines this close to each other because you have parasitic capacitances and this signal might influence that signal. Yeah, whatever. So, design browser, AND gate. Okay. Well, I know what an AND gate is. It'll only output if both of these things are high. So, I have a question. Can I make diodes in this game? Why am I not able to? Okay, so let's see here. Okay, so I can do that. Really? Really? Okay. So there's no diodes in this game. I'm peeved. Okay. So, yeah. So what you can do in the real world, the moment you have a P to N junction like this, you can have just the P to N junction by itself, instead of having like it on all three sides. Well, let's see. Does it actually do it though? I'm curious. Via down to this, and then let's do another via this way. Does it actually work though? It doesn't. Okay. Yeah, fine. My electrical engineering self is definitely getting more and more peeved. So, in the real world, what you can do is you can just have like this P to this N, and that becomes a diode. So if this goes high, it'll pull this part high as well. And if this goes low, and it'll go low as well. And the trick to that is it's like a one-way valve. It'll only electricity will only pass in one direction. So what I was thinking that I could do is I could do something, no, not really quite like this, but essentially I have two diodes going into the output, and that would be a valid solution because, yeah. Oh, hey, Juice. Yeah, so that would be a valid solution, but apparently this game does not like it when I, yeah, well. So if it's an AND gate, that means that these need to be in series. Let's go and erase this. do I want a p-type or an n-type? Well, because there's another concept I'm not gonna quite get into just quite yet. But this, yeah. So in theory, this should work even if I don't connect it to the power. But yeah, it wants me to connect it to the power. Fine. Yeah. Yeah, I guess it is also, in theory, good design, because what you could theoretically do is, what can you theoretically do? Actually, wait a second. This doesn't need to be all the way out here. Could make this like that via metal, get rid of this metal, via, there we go. So it's gotten down to 8. How do you get it down to 6? Because this game forces you to... Oh, what happens if I connect the two together? Okay, let's see here. If I connect this over here, this is very much something that you're not supposed to do. Oh. Interesting. There we go. Yeah, so... okay. Yeah, no diode. So Rolami says, it is quite limited. I agree. No diodes, only transistors. Only one metal layer, not much space, as you said. Interesting concept for capacitors. I guess I will try to keep quiet for the most part. Yeah, so there's a lot of weird... yeah, some weirdness with this coming from an electrical engineering background. Yeah, so one thing that you would never do is you would never connect two inputs together like that, because if one of them is being driven high and the other one's being driven low, you're essentially short-circuiting the two things, and a lot of current might flow through that, and you might break something. Worst case scenario, you burn something out. Best case scenario, you get weird / wonky working versions of whatever you're doing. Yeah. But another good practice is that if you know that your input is going to be like a signal input, then you wouldn't ever use it to drive the output. You would want to use the power rail to actually drive the output, and you just want your signals to control it. Yeah, mostly so you don't like load your signal path too much, because it could be really weak. Depends. Yeah, so apparently the area in this game is the smallest rectangle that encloses all of the silicon that you use, but doesn't really have anything much to do with the metals. Yeah, but let's see. OR gate. Well, we just did that. You just do this. Or... oh, okay. So it does prevent you from... yeah. It does prevent you from shorting the inputs together. It gets unhappy if you do that. Okay, fine. So I'm thinking something like, I wonder if I can do, no, okay, it doesn't like it when you do corners. This is definitely a way, but I'm wondering if you can make a smaller rectangle. There you go. Yeah, so it is theoretically possible to do it in even less size. 10. Oh. Do I see it? Oh well. So this is definitely two things in parallel. Let's see. IEEE just mentioned in the Zachtronics Discord that he expects me to tell him what metrics are good in my opinion after this stream. Yeah, this area is definitely a little bit weird. I wonder, what do you do to get this done in 10? Oh, I think I see it now. Yeah, instead of getting these together, I can wire it up in metal afterwards. I really think that's kind of weird how it's okay, I guess I can't do it in this very row. Then P-type, P-type, and then metal, metal, via, and then metal. Yeah, there you go. Yeah, one of the things that I kind of dislike about this game right now, like off the bat, is there is also ground. When you stop powering something, it's not like there's no more, like it's kind of, it's not like it just kind of disappears. It's more like you're really driving it to a low voltage. So yeah, if your signal turns off, yeah, that's okay. I'm pretty sure Constructor was a little bit more complicated than this. The playing area was definitely larger, but it was also not very well, what is it called? Not very well, it was a game that was really difficult to get into. You kind of already had to know what you were doing to really yeah, get good at it. So yeah, that game was hard. Okay, so this is verified. Oh, okay, design browser, not gate. Yeah. Yes, so you do have PNPs as well. Here we go. And then, let me make that a little bit nicer. Via. Yeah. PNPE transistors. Yep. So the idea is if you drive the gate, or in this case the base of a PNP transistor low, then the thing will conduct. If you drive it high, it will stop conducting. So with these two together, with PNP transistors and NPN transistors, or yeah, Zachtronics likes to think that these are BJTs, which is fine. But like, you could also make these, MOSFETs, and that's also fine. There's N MOSFETs and there's P MOSFETs. They're pretty much the same thing in digital logic, but when it comes to the nitty gritty of analog stuff, then things start to get weird. Okay, what is this? Reset should be high for the first 10 cycles after power becomes available on the V plus pins. Okay, capacitors. How does capacitors count for area? And can I put capacitors on top of N? No. Okay. Interesting. Place capacitors below the metal layer to create a multi-cycle delay. So I can just like do something like this, right? And just do something like that. Oh, it wants to go reset from high to low. Okay. Here we go. Okay. So that means I need at least one p-type. I wonder if it counts area like that. I don't know. Via, and then metal, this, and then that. There we go. You just cram, yeah, okay, so the capacitor does count on a size like that. Yeah, so capacitors in the real world don't really, well, it's weird. It's weird. Yeah. One of the things that you kind of that a lot of digital designers are really scared of when they start looking into like the really low level things like this is that everything is analog, because like yes, you can make these transistors and yes, they will drive things high and low, but if you put like a very large lead, like a metal that goes really far, then there's a lot of capacitance on that, and depending on how big your transistor is, like the width of your transistor, it could take quite some time for your transistor to actually charge that. So yeah, you can kind of think about it as like a delay, but it's not a delay like this, where it, every clock cycle it increments another square or anything. It's more of it's an analog thing. It's a gradual ramping up through all the voltage values up to, whatever is called high. Yeah, I mean, it's an okay interpretation of what a capacitor is. But whatever. Digital signal mixer. What is this supposed to be? Out should be high when any input is high. Okay, so this is a 4 times OR gate essentially. Here's the output. Here's V plus. Let me think about this. That's the very easy way of doing it, is I have V plus and more V plus, and then P type, P type, P type, P type, and then the output is all of those 4. That gets a little bit complicated with how this routing works. Right, only one metal layer. I could just route it over here. Actually, it might be okay if I just connect these two together. Alright, so this metal goes over here. This via. Oh, okay. There's gonna be a problem here. Let's do this first. Get rid of. Let me do that and put this over here. Does that help? Not really. Well, first I'm just going to take a look and see if this actually even works as the way that I think that it does. Okay, so far, yes. The only problem is I need to connect that all the way down here, and I've ran out of space. The concept is good. It's a 4-OR gate. Okay, so this is the easy way to fix this problem, but it increases my area. Yeah, I'm almost certain that you can do this in 5 less area, and yeah. Okay. Struggling. Don loved to explain things. So do I. He taught me a lot about integrated circuit design over beers late at night when we would meet up after work. Sometimes at a bar, sometimes at his house where he had some equipment set up. Fun times. But it was tough to make progress, partly because the work was all theoretical. Pen and paper were in my head. I needed experience, but the design lab manager at Sawayama wasn't about to let in some foreigner who didn't know what he was doing to play around with their machines. So what was a guy like me to do? Yeah. Yeah, getting experience in this field is it's rough. Yep. Yeah. So I'm kind of curious. There is another way of doing this, which is what is it called? There's this concept in digital engineering. I forgot what it's called, but essentially you can, if you have like A and B, you can make it also by doing like the inverse, like the A or B, but you like create a you put like you invert like all of the signals. I forgot what that concept is called. I feel really bad because kind of an important concept. So there's definitely there's a way of doing it that way as well, which probably involves a lot of PNP. Demoivre's THM stuff. I don't think so. What is it? Oh, it's De Morgan's laws. That's what it is. Yeah, De Morgan's laws is what it's called. Essentially, you can put if you invert the signals coming in, and then you invert the output, you can swap around OR gates and AND gates. It's De Morgan. Okay. Yeah. All right. So. Do I see a way to do this in 20 area? Yeah, that's fine. I don't see way right now. It's probably doable later, but I'll just move on. Okay, what is this? Each output should be high when its corresponding input is high. If a lower number input is high, it should block the higher number outputs from activating. Okay. So essentially, first off, this, except the higher number outputs should be blocked. Okay. So essentially, it wants to do like an and not thing over here. Let me see what happens if I do this. Yeah. And then, essentially want to drive the output of that over here. So this wants to do p-type, n-type, via, get rid of the metal, do this, connect this up over there, hold up. I don't think that works. Yeah. So there needs to be an OR gate. Let's see here. Let's first get rid of this. We can move this somewhere else. So, yeah, okay. Yeah, so what I want to do is I want to put this over there. Is it possible to do it in... Probably. Metal. This should be connected up here. This should be connected over here. Via. And there we go. Yeah, it's probably doable somehow. Oh, I see it. Instead of moving this p-type this close, it should be over here. And then you can do that. And then I can erase this via here and here, put some metal this way, and then this can finally be over here. Then via, get rid of that metal, and then there we go. Oh, except, oh, I didn't connect this up. Via. Ta-da! And that is size. Cool. Ignition sequencer. When run is activated, each output should activate with the indicated timing. Delays of 2, 4, and 8 cycles. When run is activated. Okay, I see. let me move this. So this goes to out 1. This should go to out 2. There we go. Yep, just squiggling these things around. Yeah, in the real world, this would not work at all because these capacitors would cause all 3 of these lines to be loaded with a lot of capacitance. So if this goes up, all of these 3 go up slowly. I'll let it go. Okay. Out X should be high when in A and in B are equal. Either both high or both low. So this is... what is this? It's like an exclusive NOR gate or something? Something like that. Okay, so if they're both high or both low. So let's see here. Yeah, suspension of IRL circuit knowledge. Yeah. Yeah. Should be high when alpha and beta are equal. So one of them is it's a AND gate, which we did already, which is this. Let's try doing this for now, and then we'll take a little look in a bit. So this is the AND gate, but we also need it when both are low. And both are low. Okay. I wonder if there's... no, okay. I was wondering if there was a way to drag and then... well... whoops. Is there an undo button? I wonder. Can I Control-Z my way out of this mess? I can. Thank you. Oh, I need to delete some of the metal? Okay. Okay. Let's see here. So, I want... this input alpha, yep, and then this, alright, so this needs to supply power, so I want a PNP. I want to just take a look at this output for now. Yeah, okay, so that's doing that. Okay, so what happens if I do something like this? We'll see. Oh, input alpha. Oh. Okay, so, uh, let me flip this transistor around a little bit. So, p-type this way over here. And then I want to p-type this way. Does the interface look like a real work in, it's okay, so this here, you would never use. This is, it's nice to have, but this is not useful. Um, spec, you would probably have this written down elsewhere, / you would already know what you're doing, so this is fine. The simulator, yes, you would definitely have a simulator window, and you definitely have a layout window. Though in the real world, what you would actually do is you'd have something called LVS, which is layout versus schematic. So once you lay this out, you would check this against a schematic that you've designed to actually get your spec. So there's a little bit of a a little bit of a hand wavy thing going on there, but you know it's fine. So there's an AND gate, and then I need this over here. So if I, whoops, select this, move it over here. That should work. Hey, you can do it in 12. Whatever. I'll work on that later. Okay, so just arrows. Dual oscillator. Oh. 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 That's interesting. So, how do I build this? Definitely need delays. Delay elements here. Um, hmm. What if I just... Okay, this feels like heresy. um... No, I want a p-type for this. Uh... Okay, what is it trying to do? If this is waiting a cycle, this is off, this is on. The moment this gets here, this turns on, this turns off, and then and the entire thing loses power. Okay, I guess I can't do that. What if I tried doing it the N-type shouldn't work because it should never turn on. But we'll take a look, right? Yeah, wait, it'll just never turn on. If this never turns on, then nothing ever happens. That gets interesting. So that means I need something to like kind of keep it off. How do I make an oscillator in this game? I mean, I could make like a flip-flop that constantly is getting set and reset or whatever. That seems really weird. Let's start with this PNP idea again. I feel like it's got some promise to it. What if I put 2 capacitors on here instead? Would that work? Huh. I guess. Well, I made something. I wonder why it's doing that. Okay. That works, I guess. That's so weird and janky. Oh, man. I'm like, wait, in real life, what even is this? In real life, this is just a diode connected PMOS. Yeah. Oh. Okay. Yeah, if I want to delay this, all I should need to do is just to make this even more capacitors. Via it needs to be connected to that one, the second one. No? Oh, I need one more capacitor. can do it in 15. Yeah, I guess. Safety interlock. What is this? Each output should be high when its corresponding is high and the other input is not. Oh. Wait, so each input should be high when its corresponding input is high and the other input is not. So it's like this is this and not A, and this is going to be this and not B, and if both, then alarm. Okay. That seems like it should be pretty easy for this. Actually, you know what? Let me go and see if I can compact this a little bit. I just realized that this B needs to go like that, and now I can't via properly to that. Out A is fine. Out B is fine. Both inputs are high. Well, let's see here. Oh, hello, Rex Kicks. That's okay. If both inputs are high, I can do an NPN there. Can I do an NPN there? Actually, that would work. Do something like that. Right, I need to actually route this over here. It's not pretty, but it works. Yeah. Can definitely shave down area. Definitely a lot of area to be saved here. I just need to actually go through the part where I actually optimize these things, but whatever. The hookup. That's when I got the hookup. A bunch of us had gone on a work trip to Hong Kong. While we were there, Don led me into a marketplace full of small stalls with vendors selling all kinds of electronic gadgets. Hong Kong, I'm not so sure, but Shenzhen, which is very close by Hong Kong, yes, definitely. I thought maybe he was going to get some parts or something. Instead, he talked to a guy who handed him a thick paper catalog as big as a telephone book. He flipped to the C's and found ChipWizard Professional cracked. uh, the guy in the stall nodded and yelled to another guy in the back who made us a copy right out there on a microdisc while we waited. Okay. Yes. So, software piracy and like the making of essentially illegal copies or knockoff copies is very, very common in China. Um, it's still a thing, and yeah, the honest answer is half the time you're gonna get something that's really weird, like someone bootleg recorded something. um, like yeah, took a camera into a movie theater and recorded something, or like you'll get something like um, you'll get something like somebody tried to make like a disk image, but instead of actually burning the ISO that's actually on the disk image, it's just a file that's got uploaded in onto the disk or something. Anyway, yeah, lots and lots of weird, questionable things going on, but yeah. Safety interlock, PWM solenoid driver. Ooh. When hold is activated, the coil should be powered for 4 cycles, then begin oscillating until hold is deactivated. Okay. When hold is activated, coil should be powered for 4 cycles. So that sounds like this to me right now. And it should start oscillating after 4 cycles. So what happens if I do this? Oh, I need to not put a capacitor under there. Uh. Eh. Okay. Let's go and remove this via put an N-type over here. Am I doing this right? I don't know. Let's remove this metal for now. Let's hook this up to the output, and this should just be the same thing. Now I need to figure out how to make this oscillate. After a delay, Hmm. Hmm. So I need to delay, and then I need to get it oscillating. I'm gonna go back and take a look at what I did for this oscillator. So it's just this. So I need to do this and then a delay. It's just an NPN transistor with 2 squares on the feedback. So that should just be this. But why is it not working here? Wait, did I say NPN or PNP? This is PNP. Okay, this is PNP. So why does this work but mine doesn't? This is PNP with 2 of these. Oh, because it is connected over here. Now that introduces a delay. So I can't do this idea that I had. Okay. Let's go and erase this and this. Select this and move it over and connect these back up, because I do think there is something. Yes. Definitely something that I can do. Oh. If hold goes on, I can wait and then I can start doing this oscillator. Yes, that's how. Okay, that's what it is. Something like this? Let's see here. No. Why? P and P, because it's connected this way. Okay. Let's remove a capacitor here and see what happens. So, okay. How do I start oscillating this? I guess I actually do need like a second one of. Do I? Yes. So it's just this oscillator needs to go into feedback mode. Hold, delay. So this oscillator. Yeah, okay. So does this work? I should not optimize this early on. That's just a recipe for not success. It's just one of these things with the capacitor and the feedback. Oh. So I need more capacitors here. How does this oscillator work? On means this needs to turn low. Or it needs to turn off. Yeah. So this really should be over here. Like right there. And then this N type can go like that. And then delete this. This metal needs to go over here, there, N type via there, metal. Oh, and that should work. Or it doesn't. Why? Oh. I guess it's supposed to be that one then. Whoops. There we go. Let's see here. There's definitely ways to optimize this. This is very, very much not optimized. Yeah. Yeah, I can very much definitely get this smaller. But we'll keep going for now. Electronic lock. Low, high, high, low, high. Let's see here. Low is 1 and 4. What? I have to do this and then drag the N over it. Okay. So let's get that done. Could also just do this and move this up. That's fine. Low, high, high, low, high. There we go. So all this is I have a bunch of AND gates really. It's all in series. So this open signal only goes high if all of these gates are conducting, which means this needs to go low, this needs to go low, this needs to go high, this needs to go high, and this also needs to go high to power the entire thing. It's the most simple, straightforward way to solve this that came to me anyway. But yeah, it's apparently possible to do this in 12. Whatever. The 12 here is interesting / nice. Yeah, it probably is. Motor controller. Let's see here. The 12 is visually pleasing. Inputs on and off. Outputs motor. When on is activated, motor should be turned on until off is activated in a later cycle. Okay. Yeah, so this is essentially make a set reset latch / flip flop / something. Okay. So I need to make something that is self-sustaining. Oh man, I'm thinking of a SR latch thing again. Which really is just, this is positive feedback. I wonder if I can make it like this. Probably. Well, let's see what happens if I do this. Okay, nothing happens. Okay, what if I, instead of putting the via there, I put the via there? Then what happens? Okay. Also nothing. Alright. Why do I put a capacitor? Okay, it's a completely separate thing. Cannot do anything with that. Okay. So, if I have an NPN transistor like this, and this wants to go high. If I have a PNP transistor like this, to turn this on, this needs to go low. So this wants to go high. So this needs to be fed into that, and this needs to be fed into that, which is what I just did. Alright. Guess, alright, I'm also forgetting there's power supply stuff. Let's... Actually, technically, I don't need that. I could just metal this way too. That is a diode. That is a diode connected PGAT. Yeah, you do have diodes in this game. They're just bad diodes. Can't make them two squares. Alrighty. So if I want to do this, so I turn this on. This needs to remember that it's on. How does that work? How does that work? Because I feel like the moment I cut power to anything, it's just going to die. If this goes on, what if I did this then? Okay, so I definitely need a capacitor somewhere because that's this game's version of a delay element. There's supposed to be some kind of feedback loop then. And it needs to be powered using V+. Yeah. How do I think about the way capacitors work in this game? It's not like real life capacitors, is it? Yeah, I mentioned this earlier on stream, but it's a very interesting take on a capacitor. one of the earlier puzzles that wanted me to make like a delay of 2, 4, and 8. Um, I had a lot of questions about that because yeah, if you actually did that in real life, all of the capacitors that you put in a row, they all get charged at the same time. Uh, it gets charged slowly if your input impedance is high, aka your whatever is driving your circuit isn't very powerful. Um, so yeah, it's a interesting take on a capacitor. Let's just leave it at that. uh, let's go and I want to erase this and move this up a little bit. So I feel like if I do this, actually, let me. Yeah, so I've just made an inverter. Although this could just be there anyway. Um, and then I put a capacitor on this to feed it back. What happens if I do this? I'm guessing real-life circuits assume all signals are instantaneous and rely on clock cycles to create delay. Um, there's a few things to pick apart there. Signals, for all intents and purposes in digital design, you can assume that they're instantaneous. If you're doing something like on an FPGA, the thing is already designed so you can kind of assume that, okay, if I turn this from a 0 to a 1, then the next thing is going to see it. So yeah, you would be using delay elements, which are essentially like a single set reset latch kind of thing to create a single cycle delay. That's something you would actually like build as like a block, and you just use that everywhere. That's called a standard cell, by the way. Yeah. Things get a little bit weirder when you start talking about really high frequency things, because when you start doing really high frequency things, for example, radio frequency, your your signal doesn't actually travel instantaneously. It travels at somewhere around the speed of light. It's not quite the speed of light. It depends on things. It actually slows down a little bit. It's not quite the speed of light. But electrical signals actually travel at, yeah, yes, transmission lines. But yes, your signal doesn't when it propagates down a wire, it doesn't do so instantaneously. It's limited by speed of light things. So if you're clocking things at really high frequency, then that kind of starts to become a factor. How high frequency are we talking about? I believe for a megahertz, like tens of megahertz signal, the wavelength of that is around the order of meters. If you start talking about gigahertz frequencies, then it becomes the actual like wavelength of the signal that's going through your wires gets down to like a few centimeters or even smaller. And of course, if you start talking about terahertz frequencies, which is starting to get into the light regime, then that's on the nanometers. Yeah. Oh, so 1 gigahertz is 30 centimeters? Yeah, okay. I'm going to trust IEEE on this. But, yeah, once you start clocking very, very, very high frequencies, then you start to have to take in. You start to have to be careful of, like, yeah, my signal doesn't transmit instantaneously, but that's mostly a problem if you're doing like radio frequency engineering, because that's when you start to deal with very high, um, what is it called? Like very high um, frequencies and pretty large things. So yeah, you start to be like, okay, if I try to oscillate this signal at 1 gigahertz and I have a thing that's like 1 meter away, I'm gonna have like this weird delay in this transmission line. Um, it might be a problem. It might not be a problem. It depends on what you're using it for, of course. So yeah. Um, real life circuits assume all signals are instantaneous. A little bit of a caveat. Yeah, if you're doing very high frequency stuff, you can't assume that they're instantaneous. But if you're doing anything that's like below like 50 megahertz, really 20 or 10 megahertz and below, if you're doing anything below that, then you don't have to worry about the propagation speed of signals. You don't need to worry about that at all. So yeah, for that you can assume that all signals are instantaneous. And yeah, you would be relying on like latches or flip flops and that kind of thing to create delay cycles for things like this. Yes, good question. Good question. So what I want to do, the idea that I have right now is, I'm supposed to create something that keeps itself off to remember. Yeah. In general, if the size of your object times frequency is less than 1/10 of the speed of light, you can neglect it. Yeah. Yeah. So, yeah. Quick side note. If you start to work with half wavelength frequencies, like for example, 1 gigahertz is 30 centimeters. I'm guessing that's actual wavelength. If you're at 15 centimeters, that means there's already half of a wave in there. So this already has gone up and gone down. I have not actually played too much Constructor for Rex Kicks. But yeah, if you start getting, even if you're at half wavelength, things will get a little bit weird. So you have to make sure you're much, much smaller than your wavelength of interest for you to be able to make the assumption that, things are instantaneous. Yeah. All right. Yeah, I mentioned Constructor on stream a little bit ago. I did not go very deep into Constructor. It's rather hard to get into, but yes, I have played it a little bit before. Back to this puzzle. Create. Yeah. So I need to create a latch. Something that remembers. It needs to positively feed back into itself with the ability of being turned on and turned off. It needs to be bistable. The question is, how do I make this bistable? This is on. I want to turn this. Okay, I think I'm gonna try to start from. Yeah, so a bistable circuit is like it. How do I? It's kind of like a terminology that's in contrast to something that's monostable. So, for example, if I had a capacitor with a resistor in parallel with it, so it's constantly draining this capacitor, and then I have a diode to it. So if I did that, what would happen is if I pulled the input of that high, then what would happen is it'll charge the capacitor very quickly because a diode is pretty low impedance, and then when I turn my input off, it will slowly discharge back down to 0. So it tries to go back to one set state. That's why it's called monostable. So even if you you pulse it up a little bit, and you turn off the pulse, then it will always try to go back to where it originally came from. There's only one stable state in that kind of system. For a bistable state, it's kind of like there's two stable states of the system, and the idea is you can switch back and forth between these two stable states. But if it's in one stable state, it wants to remain there. And if you switch it to the other stable state, it wants to remain in that other stable state. Yeah, so it's an interesting little bit of a problem. So the question is, how do I want to do this? The problem that I have is that the moment you cut power to anything in this game, everything dies. That's the part that I'm still trying to wrap my head around. Yeah, it's a SR latch, yes, a set reset latch. Yeah, there's ways. I don't remember exactly how to make an SR latch, schematically speaking, which is why I'm struggling with this puzzle. I'll just quickly search it up. Yeah, I guess I'm cheating a little bit here. Let's see. Let's see here. Traditional flip-flop. It's 2 transistors. Yeah, it's something like 2 exclusive OR gates, but that's more of a abstract. Once you start talking about this kind of thing, then things get a little bit more complicated. Because at the end of the day, it's still kind of, yeah. My first plan of action is I want to first see if I can create this into some kind of feedback loop. So this goes on, and I want this. Let's see here. So if this is on, then this should be off. This should be on. So then I need something that turns on. That to turn. Okay, let me go and V metal over here. Via here. Erase this. And metal this way via there. So this should be off, and this should feed back into it like that. So, okay, so that's what it doesn't like. Yeah, this is with how it's wired up right now, this is not a stable circuit. Okay, so this is how it should work. Yeah, and then I can do something like this, and then it'll turn on and off. Oh, okay. But I need to isolate this. Okay, fine. Oh, that was funny. Okay, so I need to isolate this from this. So I need this to be an NPN diode kind of thing. So let's do It's now the point where we mentioned both sides of your circuit are high. Yeah, so that is, those are the power rails. That's fine. That's supposed to happen. Okay, I have to do something like this. And then this needs to go over here and also connect to this. But yeah, well, yeah, the on is gonna be turned on all the time because it's gonna be doing this. Okay, so I want this to set it over here. The question is, how do I actually isolate this? Whoops. I could isolate it by using this to turn it on. So an NPN that way. Let's remove this capacitor. Question is, does this work? Okay, so I need to add a capacitor over here to make it stable. There we go. And then, similarly, I should need something over here. Man, isolating these inputs is rather annoying. Because, yeah, what I really want is another thing over here. But I could... Yeah, let me go and compact this a little bit. So let's go and get rid of this. I need a p-type like that. This should do this. Get rid of this metal. Put a via there. Put this metal over here. And this via should go this way. Then Okay, so that works. The only problem is I need to somehow extract my signal from all the way over here. Oh, whoops. Did not think about that. I see it. Do I? Do I see it? There's a... it pains me to do this. It's very not optimized, but it's fine. Then metal... There we go. That is very messy. Yeah, definitely there are better ways of doing this. 12, interesting. Yeah, making these latches. Let's see here. Is there... Yeah. I'll go back and take a look at the next one. Programmable delay, synchrony detector, and or combo gate. And then there's 3 more. So we got 6 puzzles left, I think. Okay. The alarm output should activate n cycles after the run input, where n is determined by the currently active time input. So these are not... Yeah, these are never on at the same time. Okay, that's easy. So run. Running out of space here. I can probably do an n-type this way instead. Or yeah, I have to. Otherwise, well, do I have to? I can get rid of this. If I do it this way, yeah, I could. I can just do it like this. And then get rid of this metal. And then that one needs to be delayed even more. Except I've run out of space. Need 2 more delays on there. 1, 2. Is that good enough? Here, let's see if I can squeeze in 2 more. Oh yeah, okay. There we go. Get rid of this. P-type over here, via there, via, and metal it up. There we go. Yeah, that's pretty big. Definitely, there should be ways of getting this smaller, but... Excuse me. Synchrony detector. Oh, boy. Oh, boy. That's an interesting problem. Flamanus says, can I point out one thing with that level? This level or the previous level? The previous one. Yeah, sure, go ahead. Oh. Okay, well, take your time. But yeah, there's definitely better ways of doing this level. This is a messy, it will get the job done kind of kind of solve here. Yeah, because like in theory, this junction that's over here that's connected to alarm, yeah, theoretically you could actually combine all of it into this one square right here, but my 3 inputs are mutually exclusive. Yes, yes they are. Hmm. Yeah. Yeah. Oh, I see. So what you're saying is just to do this, and then remove all of this. That's very janky. That's incredibly janky. And, yeah, I'll put that into oh, I guess I can't copy over design revisions. It doesn't feel right to me, honestly. Yes, in theory, um, but like, yeah. There's definitely, if that's the case, yeah, there's a much better way of doing this. Um, let's see here. Is this the way that I want to do it? If I actually have it bent, it's actually kind of nice, but um 1 too much delay on that. Yeah. Let's see here. If I put a capacitor there, I can put this metal here instead. Then I can do this. One too much delay. Whoops. Here. $20. There almost definitely should be a way to move this over here and save 4 area. Yeah. This is pretty janky. I'm trying to figure out how to actually do that. Because there's definitely is space this way. Yeah. Question is, how do I actually get it over there? 18 is known, 16 hasn't been found yet. Huh. Interesting. Interesting. There we go. Well, that's fine. Synchrony detector, and or combo gate switch debouncer. I'll take a look at this one first. Okay, so what I know is I need at least 6 capacitors on this to hold something high. The question is, how do I make it not trigger on subsequent things? If I do this... That sounds almost like a latch thing, but I'm gonna let that brew for a little bit longer. Oh, this one seems easy. Let's do this one. If gate is high, then it's an AND. Okay. This is high. If gate is low, then it's an OR. Well, this is the AND gate usage right now, and it works. If it's OR, that is low, then this is OR. So then I need to do... Actually, let me go and erase this metal here, select all of this, move it down a little bit. So I can do this. And then this goes over here. And this p-type. Let's see, how does this work right now? An OR gate. I think it'd be better if I just did something like this and then put this N over there. Yeah. So the question is, how do I do this OR? If this is high, then I want this to be... Oh. I can do this as an OR gate. Move this metal all the way over here. Oh. Like that. It's not very pretty, no. I don't need that, actually. Because I could just... diode connect these. Oh no, I can't. Then I'd be shorting the... wait. Ah! Eh. Okay. There we go. And then I need to suppress this output whenever that's that, so I can do... yeah, okay, I guess I have to do it that way. So this gate needs to go down here, via there, via here, and then this needs to be, instead of the vias being up here, I need to put the vias down there. Can I do that? I might be running out of space. No, I won't. What? What? Okay, it's like this cycle. A and B turn on at the same time and weird things happen. Why? Why is the gate flashing? So this is turning on, this is turning on, that turns this on. But the gate is off. Oh, it's because of this. It's making a loop back around this way. So if I get rid of this metal, it should be working fine for this, and it doesn't work for the and. And if I get rid of this via and I connect it over here, it should be working fine. Except my inputs are not working fine. Why? Input A wants to go low, but it can't go low because... Oh. Because this is... Alright. So things are a little bit more complicated than I thought it was going to be. Alright, let's do this first. So this is an AND gate, and that's fine. So there's the triple AND. This is fine. Then the question is, when it goes low, what do I do? Then it needs to be an OR gate. If I connect these two p-types together, it should be unhappy because I'm shorting alpha and beta to, yeah, A and B together. So I need to isolate these. What if I got rid of this, selected this, moved it up? Okay, well, whatever. This should work. Now I need to do an OR of these two, which should be doable just like this, but it might lead to the, yeah, it leads to the same problem. So with this better layout, can I get this to work? Is it the same problem if I do this? Or does the V plus stop it? No, it doesn't. Okay. Okay, so this is the main problem over here. Oh. Oh, I see. If I do a diode connection over there, that should solve some problems. Yeah. So if I do that. Now the problem is, oh, okay. Well, Okay, so I need to connect this up to V+, or technically a diode connection would work. There we go. Yeah, I just had to go and... Yeah, there's definitely ways to save on some area. It's almost... looks very close to almost be possible in 20 area here if this is straightened out. But the problem is, it might be doable. The problem is, this needs to... I wonder if I can... No, I can't connect the p-type over there. Yeah, okay, well, this is at least easily doable in 25 area. All I need to do is via up here, and then same thing over here. And then get rid of this metal. Yeah, 25. Oh. What? I guess not. I guess I actually have to use that then. That's fine. I can't just do this. How am I doing that without power? Because you can use the inputs as power, essentially. Yeah, that works. 25. Yeah, this one junction here solves the feedback problem because the gate will turn off and prevent the output from driving back the gate and messing things up. Yeah, so that's how that works. Okay. Am I ready for the synchrony detector? I don't know. Switch the bouncer. I'll take a look at that later. Stepper motor driver. Can't you connect silicon at a 90-degree angle? You cannot. I really wish you can, but you're not. You can't. It sucks. Yeah. It doesn't allow you to do this. It only allows you to do it at 180 degree, or like, you know, like this. This won't allow you to do it because there's nothing over here, and you can do this, but yeah. Yeah, it is really sad. Alright, synchrony detector. So how do I detect the rising edge? I probably don't need to overthink it that much, but like, is that not like real life TM? Well, okay. The truth is, you can kind of do whatever you want in real life. It might not actually work, but in real life, in real life, you generally want to make things be like this, where you have it crossing like this. Um, the one difference, though, the one crucial difference is, um, what is it? In real life, you can do more interesting things. Oh, right. The big thing is that in real life, when you try to make a BJT on an integrated circuit, you're not actually layering things on top, like this. If you look really closely on this visualizer, you can see that the N type goes on top. Yeah. So a BJT is a bipolar junction transistor, and the way that it works is different than the way that we than our normally like than our computers work. So a, a pretty much in modern day, everyone has gone off to make MOSFETs. The reason why is because a MOSFET actually looks like kind of like this, where you have like some silicon, you have a gate on top of it, and you either turn the gate on or you turn the gate off. And it's really nice because when you turn the gate on, it's essentially like a capacitor where you charge it up and then no more current flows, which is super important, because it means that you're not burning power even when you're not doing any computation. BJTs, on the other hand, if you want it to remain on, you need to be constantly giving it current. It's constantly burning power. So that's why people really stopped using the older style of transistor, which is the BJT. But the way that this game likes to think about and work with transistors is kind of like a combination of BJTs and MOSFETs. It's a little bit weird. Yeah, because in the real world, if you actually try to make a bipolar junction transistor, you don't actually make it like this. This is what a MOSFET transistor would look like. If you wanted to make a bipolar junction transistor, you would actually like dope your silicon at different depths. It's really strange that way, but you essentially dope it at different depths, because you have your emitter, which emits some particles. You have a base which controls those particles, and then lastly you have a collector which collects the particles once they've been modulated by the base. And that gets really weird and funky because the very first thing that you notice is that they're not actually symmetrical devices. Yeah, bipolar junction transistors are not symmetrical because the collector and the emitter are doped differently. But in this game, they kind of make the assumption that it doesn't really matter. Like the emitter and the collector, they're kind of the same thing. On a MOSFET, a MOSFET is actually symmetrical. A MOSFET, the two sides that are not the gate, those are actually identical in most cases. Yeah, that was a very very big tangent. Yes, let's see here. How do I make a rising edge detector? I don't know. What happens if I feed this back into itself is my question. It starts oscillating. Oh, it instantly says you can't have this. Okay. So if this turns on, yeah, that's a question. How do I actually detect a rising edge in this game? So edge detectors are pretty important in a lot of things, a lot of digital things. But I, as a analog designer, I don't actually know what the heck they do to actually do a rising edge. Well, the way that I would do it is you would do a high pass filter, um, and do a high pass filter, and then use that to trigger something. But the problem is there aren't any high pass filters in this game. Um, could I make something that emulates a high pass filter? Um, I don't think so. I don't know. Hmm. Oh. Oh, I see. Oh, I see. Oh, okay. I'm starting to understand now. I need to stop thinking about things in analog and start thinking of things in digital. Essentially, this is high when both A and B are high, but the moment it stays on for a little bit longer, then you want to turn it off. Okay. Um, that's okay. That's a very strange and cheesy way of thinking about this. So, first off, let's do an AND gate, which is just going to be this. And then, the moment I wait any additional time, I want to turn it off. Let's see here. I can move this capacitor down here. Move this metal over here. Do an N-type there. N-type here, N-type here. Put a via there, put a via there. Delay there. Do this, and then do this. Oh wait, no, that's V plus. That's not alarm. Via there. There we go. Yeah, you can. Oh, okay. There's an easy 16 in here somewhere. Yeah, I think. Yeah, that's the easy 16. Except it doesn't work. Oh, because I messed this up. Via metal. Ta-da! And yeah, I guess you can. Yeah, there's definitely a way of simplifying this so it gets easier or it gets smaller, but good enough. Serial number ROM. When read is activated, The data output should communicate the indicated pattern. High, high, low, low, high, low. And then remain high until read is deactivated. Okay, that's just a bunch of delays. That is easy. um... Hmm. Oh. What I can do is make that diode connected. Eh. And then you just go high, high, low, low, high, low, high. And stable at high. Okay. What if I just... Okay, and I just need a diode connected. Okay, how do I do a diode connected PFET again? It is... right. Via there, N-type here. That messes up my area so much. No, I don't need that actually. Oops. Via there, and then I need to diode connect over here. So I need a NPN. There we go. 24. Alrighty. Yeah. In the real world, you would never hard code something like this into silicon. I guess if it's for the serial number ROM, then maybe, I guess. But that's so... It feels so weird and janky to be doing anything like this. I wonder if there is a better way of doing this. I don't know. Maybe. Maybe not. I'm not sure. If I flip this around, Would I have enough to route that way? I don't think so. I don't know. Alright. Stepper motor driver, pulse echo detector. So I've got 3 more circuits to do. Pulse echo detector. What the heck is this? Out 1 should turn on when the first pulse is detected. After that, out 2 should turn on when the second pulse is detected. Both outputs should turn off when the oh. Okay. So first pulse so this is another memory thing, except I need 2 bits of memory storage here. The pulses are only 1 length, always. Okay. Well, let's see here. The moment pulse turns off, then everything is going to turn off if it's only powered by pulse. So I will need some kind of something like this. So if I invert the signal, then the moment this turns off, everything here is going to get cut, which means right, so out 1 needs to be pulled high then. Yeah, actually, I'm like going back to doing this. I could just take a look at my where did it go? Motor controller, electronic lock, is that what it is? No, it's not this. It is the... Was it motor controller? With the... Yeah, okay. Yeah, it's this. The latch design. So this is 2... This is 1 bit of storage. This is a very bad design. But anyway, yeah, that's not really usable here. This is too big for what I need to do. Okay. Let's see here. Out 1 should turn on when the first pulse is detected. After that, it should turn on. Out 2 should turn on when the second pulse is detected. So I need some kind of data storage. The question is, how do I make this actually work? Is it possible to make that data storage much smaller? If I turn this on, this is going to go high, which means I want a corresponding P to go low. This P needs to turn something else. Let's see here. What happens if I do this? That's funny. Okay. Okay, this is just an inverter because of this. The question is, how does this feedback actually make any sense? I don't think so. Whoops. What if instead of this I did metal over here and then a via there? Nothing, because it's all blocked. Oh, essentially what I want to do is essentially make like a delay circuit that is kind of self-sustaining. Pulse, yeah. And then that's the output. Okay, so if I feed this back to itself, what? Oh. Now it turns on and it stays on. Okay. Let's see here. I also want to be able to turn that off. Which means I need a way to cut power to this. Okay, let's see here. This footprint here is not being used. There we go. And then we want essentially this thing again, but it needs to be triggered from this pulse. That's a bit of a problem. Is there a way to compact this? There probably is. Like moving the gate over there. But then that would need to route over here. Maybe not. The problem with this is that it's going to turn on everything. And if I put a delay line there, it doesn't help because it only, whoops. Undo. So what I need to do is when this is on, no, when that is off, it should prevent this from going. But then it's just gonna... Oh, wait a second. I could delay that. If I turn this over here, I can move that over. So if I do this and then do this, I can put the via here, and then I could get rid of this. Now this is not connected to each other. Um, Wish there was like a rotate tool. But yes, I do think that this capacitor here is really important because I want to drive the output from that. The problem is I need to move that signal across all of this. Oh, wait a second. Why am I doing it like this, though? If I pulse and I can turn this off. This power supply situation here is really bad. That's my biggest problem. How can I alleviate this? I could use this power supply here, but if I do that, I have to route around this. Is that okay? And this needs to sustain itself. Why aren't I just doing this? Yeah, so right now the only problem is this out 2 doesn't sustain itself. Um, But I'm getting pretty close to getting this working. Okay, let's see here. What is there to be done? It's this circuit here that works really well. It's like this donut thing with yeah. Don't quite have enough space, but I should be able to cram this in. Um, is that possible? Maybe. Maybe it is. And then once this is self-sustaining, that should also be self-sustaining. Except it doesn't work. Why? What? What? Oh, come on. I need 2 delays there. Because the pulse turns off on this next cycle. Yeah, sub-cycle problems. That's so dumb. The issue is, do I even have... No, because that'll delay that. Other than that, it's fine. Okay. Yeah, that's a problem. I don't have the space to do that here. So if that would turn this on, then that would feed itself back. What if I did this to do the feedback? Would that solve any problems? I don't think so. I just need to make this more compact. Ooh, I might be able to see a way to do that. Maybe. All right. Time for some more floor planning. So I need 2 delays. Oh, yes. Yes, Rex Kicks. I'll see you later. Have fun with your stream. Okay. Stepper motor. Alright, see you later. Discovering the different good motor controller solves after the level being so convoluted. Motor controller. Oh, this. Okay. Now, theoretically, it is possible to do it that, like how I had it this way with the O and the two things off the sides. But I need two delay elements in here, which is just horrible. What if... Okay, so two delays I can do over here, and then do this as a via, and then all I need to do is to do that. Or this. I think this one, I think this is actually the right place to put this. Yes. And then there's another thing to do it over here. Problem is, I need to route this somehow. Because that needs to feed back into itself. Okay, let me try doing just this for now and see how it goes. Right, power. Right, it's not sustaining itself because this needs to go do something like this. Why? Because this also needs power. I can't get it over there. That also needs to be connected up over there in this case, and the problem is I've completely cut myself off by routing both silicon and... Okay. Alright, I think what I need to do is start messing around with this area a little bit more. Because that is certainly doable in less area, which means this should also be doable in less area. What if I did this instead? Like that. Then I should be able to metal over here, via there, via here, metal across like that. Except the out 2 because I disconnected that. And there we go. Doable in 25? I guess. Yeah, that was a tough puzzle. I enjoyed it though. Yeah, this is a interesting thing. 2 more. Switch debouncer and stepper motor driver. Doable in 24. Really? 24 would be... Oh, that's 6x4. Okay, yeah. I know I can move this up a bit, but I'm not sure how... Well, I can see that this could be simplified a little bit. I'll take a look at that later. Switch debouncer. Oh. Well, well, probably should have done this one first. And then you just put this on a giant delay line. I can probably make this smaller. could turn this upwards too. Oh, wait a second. That might oscillate. Oh, let's see. Let's see what happens if we do this. Oh, it does work. Neat. Doing this in... I can see if it's possible to get it done in slightly less there, but... Oh, yeah, of course it is. I can do this, do p-type like this, and then via here and here, do a metal like that, and then this, actually that might be a little bit, yeah, sure, let's, no, graph theory reason says that's not going to be possible. 1, 2, 3, 4, 5. Whoopsies. Yeah. That's weird. This is the same thing. I just need an additional capacitor, which is what makes that too much area. Whatever. Yeah, I mean, this one is much easier to do once I've done that. Stepper motor. Okay, what the heck is going on here? Should oscillate with the indicated timing. Oh. Okay. Yeah, this is an interesting one. I think this is the last one, too. Yep. Okay, let's see here. I think I first want to start off with one of these things that can feed back into itself and create an oscillator. Probably with a few delay elements. what does this look like right now? Okay, need one more delay element. And I can make that also really easily. But I first need to go and flip this around because I've cut myself off from access of that. Does that work? Well, that's one thing. And then the other two. Because I was doing the reset, and it needs these four. The other thing is I need I need to get this delayed by a slightly different amount. That's all there is to it. Except when this cuts off, it's gonna be a little bit more abrupt than it should be. Oh, it's supposed to be B minus. Yeah. this is definitely a very preliminary design. I don't expect this to have worked out as well as it has, honestly. But I could simplify this. Yeah, why not? Is that right? It's slightly more complicated. Let's just do it this way. Because that red there needs to go all the way up over here. That's a problem. Is it a problem? Okay. I need 2 delay elements there. But it also doesn't really work. Because this isn't completely symmetrical. This juts out a little bit too much. It can't be mirrored over here or rotated over here. And also this needs to go over here. So, Yeah, I need one more delay element here, which I might be able to fit in if I do it this way. No. This is tricky indeed. What if I did it that way? Well, let's see here. This is... oh wait, I can just do this. Put a capacitor right there. There we go. And then I can just mirror the... can I mirror it? The minus and the plus are in the wrong positions. Let's just hope and see if this works. Fine, I'll die. Alright, so that means that this part needs to actually go over here. Okay. There should be... I already have some resonances here. I don't need to create a whole new one. So I already have some oscillation going on here. So this here, hmm. And the problem is, I've completely neglected out B positive. But I do see there should be a way, because this is already controlling a bunch of stuff. Um, if I had like another, actually no. Um, hmm, this isn't going anywhere because what I was thinking of doing was this is two transistors that essentially logic out getting this. But if I wanted to make all of that, I would need four transistors total, and there's like hardly enough space to do that unless I'm really clever. Um, oh, I could. Hmm. One, two. Yeah, no, there's not space unless I get combining things. Yeah. That's positive minus minus. Okay, so this capacitor, I was trying to hope to use it as kind of like a one-way only thing, but that doesn't really work. So what I really need to do is I actually need to make a diode. It should look something like this, but this is definitely too big. And now I don't have anywhere to get this done. Do I? Or is that a lie? If only, if only. Oh, that is so janky. That is so janky. Okay. The art of design. So where'd my engineering career go from there? Yeah, about that. All I say is, if you're reading this, you've gone much further than I ever did with the program. But I think it was important that I tried my hand at it and got to know what the folks in the design lab were doing all day. It gave me a real appreciation for that kind of work. Because of my personal experience trying to design chips, I realized it's not always about maximizing power. Sometimes a good design is truly artful, and I'm thankful I can see that now. Alright. Yeah, so, yeah, thanks and sorry for making you sit through that, Rolomni. Yes. Um, Honestly, chip design, when it comes to layout, there's definitely, um, it's kind of like Space Chem in a way, where the really top-notch solutions in Space Chem, they really like you can tell that something is going on that's just magical, and you can tell that there's a certain elegance to it that everything just kind of fits together and it's logical from start to finish. And it's kind of similar when it comes to real life chip design. There is sometimes a elegance to certain designs that you once you look at it, it stands out very quickly. And it has to do with, because with if you're trying to do things automatically like auto routers, there are like what it'll do is it'll just wire everything up horizontally and then it'll wire everything up vertically, and it just kind of iterates over and over and over again until it kind of works. And an auto router is very useful, especially in digital design, because you don't have to worry too much about like little optimizations and whatnot. So they're fine, but you definitely lose something there. And when it comes to analog chip design, there's certain things where it's like when you design the circuit itself on a schematic, and you try to convert that schematic into the actual product, there is a almost like a there are some points in the circuit where you have to optimize for certain things. For example, if I'm making like a bootstrap circuit, which is something that like essentially takes some voltage and or some signal and it shifts it up like some certain voltage, you have to be really careful of the amount of capacitance around the upper end of the circuit, because you can very easily like lose a lot of your potential, or you can lose a lot of your voltage doing this if there's a lot of parasitic capacitance at the very top. So in that case, what you want to do for layout is you want to be really careful with minimizing the amount of capacitance on that very high end part, that high end node. And if you want to do that, then layout is where you have to be really careful. What you want to do is you want to essentially, in that part where you want to minimize capacitance, you want to cram those things as close as they possibly can go, and that makes it so it has very little capacitance. And that's not only just for like a small part, right? You can apply the same kind of logic for a whole bunch of different chips. And if you do that, then you get to the point where there's just so many ways that you can optimize things and how you can fit one part into another with, like, say, when you're designing on like a full chip and it's made out of a whole bunch of little parts in there, it's kind of like you have to fit all these things like little puzzle pieces into it. And also another thing is when you're actually making these kind of things in the real world, you have to be careful of something called mismatch, where you can draw two transistors that look identical, but when you actually make it, they don't turn out to be the same. So what do you do about that? There's certain techniques that can help you reduce it, but actually completely getting rid of it is kind of like I would almost say that it's a holy grail if it weren't even more difficult. A lot of it has to do with the manufacturing side of things. If you can somehow come up with a process to make transistors where there is absolutely no mismatch between transistors, like, you can do some pretty magical things with that. If you can somehow make a process that creates transistors without any mismatch between any two transistors on the chip, then, oh lordy, you have just hit, like, not even a gold mine. That is, like, so valuable. It's much more valuable than even gold, is what I would say. Probably worth billions of dollars if you can if you can make some kind of process where transistors have no mismatch. Because one of the biggest problems in analog integrated circuit design is the problem of mismatch. Um, if you want to copy a current from one part of a circuit to another part of a circuit, you use something called a current mirror, and that has mismatch. You have mismatch in the transistors between the current, between one side of the current mirror and the other side of the current mirror. And if you can somehow get rid of that mismatch, oh man, like the amount of accuracy you can get in analog electronics jumps up by a huge amount. If you want to do things like, say, if you wanted to build a operational amplifier, which is like the base kind of building block of analog computation, those things are limited in their accuracy by the mismatch of these transistors. For example, if you want to, an operational amplifier really just takes two voltages, compares them, and like amplifies that difference. The problem is, because the two transistors at the very start of this device are not the same, there's an offset voltage that gets introduced into this. They're also not ideal because they actually do need a little bit of current to bias it properly, but the main problem is, because there's mismatch between these transistors, it doesn't behave like how it should, like ideally. What happens is there should be there's supposed to be there's an offset introduced. So to actually make it adjust back to its ideal operation, you need to add a little bit of a voltage in one way or another, just because there's mismatch. And if you somehow, again, if you make a process without any mismatch, you can start doing some really, really magical things. For example, you can generalize this idea of a differential pair, which is where you essentially have two transistors and you're comparing like what the voltage is on each of these inputs. And instead of just doing 2, you can add more to it. You can do 3, 4, 5, 6, 7, n. And what you start to see is, if you try to do that, well, number one, it doesn't really work that well in the real world, only because the reason why it doesn't work very well in the real world is because the mismatch between these transistors, if you keep adding more and more and more of them, there's so much mismatch between them that you don't get anything useful out of it. But in the ideal world, if you have no mismatch, oh boy, you've just kind of solved the sorting problem in O of n time, because you input all of your elements into one element per transistor in here. You put the voltage into that, and your common node is going to bias all the way up to your highest voltage, or right, it's going to bias up to about the highest voltage, so you can extract the highest value in your array just by running this machine once. And then you disable that input. So now you can just spaghetti sort this whole thing in O of n time. So you can do some really magical things if you can somehow solve this problem of mismatch. The circuit that I described, if that's something that's of interest to you, it is called a winner-take-all circuit. It is something that I learnt in a class called Neuromorphic Analog VLSI, where there's certain structures that are like this in the human brain, and what you can do with this is pretty magical. Pretty magical indeed. Yeah. So if that's something that's interesting to you, Dr. Hassler does have a open website. Uh, if you just search up ECE 6435, there is a winner-take-all circuit in there. You can, in ideal case circumstances, in ideal cases, you can use it to sort in O of n time. There's all other very interesting things that you can do if you decide to go down this rabbit hole of circuit design. But yes, overall, my thoughts. Yeah, it is somewhat reminiscent of real circuit design, but there's certain differences that that instantly pop up as, okay, this is a little bit definitely not how things work. First of all, the capacitors, they look like they're just on the silicon surface, and it's just like, okay, the in the real world, capacitors in an integrated circuit like this is made by putting a what you're really doing is, all right, so I gotta quickly talk about MOSFETs right now. You've got the silicon, which is the base part, but to actually control how the signal goes, you have like an oxide layer on top of the silicon, which is kind of abstracted away in this game, / you're using BJTs. But the visualizer here makes it look like you're actually working with MOSFETs. So if we talk about working with MOSFETs for now, what you're actually doing is there's an insulator, a very thin insulator between your silicon and whatever you put on top of it. And what you do on top of that is something called poly, which is short for polysilicon. Yes, in the olden days, what you would normally do is you would actually use a metal layer to actually put on top of this insulator, and that's what you use to control like the N and P's. So that's essentially what this is. You've got this, which is in the actual silicon, but to actually do this kind of controlling gate here, what you would do is you would actually have an insulator across the entirety of the silicon, and then you put a piece of metal over top of that, like a strip of metal this way. And that is what you actually use to control this signal. In modern times, we no longer use metal to control this. The gates are no longer made out of metal. Instead, we just use more silicon. But it's a special type of silicon called polysilicon because it's polycrystalline. Because we don't really care about the crystal structure of this gate, the controlling part. The silicon wafer below is definitely one giant single crystal, but on top of it, it's poly because it's not as critical. Now, what do you do with that? So, why is that important, and what do you do with that? When you do something like that, it means that, well, number one, because there's an insulator, absolutely no current flows through the gate. Well, not quite absolutely. Quantum tunneling is a thing. We're not going to go into that. But you have pretty much no current going into that. But the gate there is capacitive. You do need to actually drive this gate either high or low, because when you have this overlap of the metal / polysilicon over top of this conducting piece, what you've really made is a conductive plate below that, and you have a very, very thin insulator. That is essentially the classic, like, textbook definition of a parallel plate capacitor. Now, the reason why this becomes important and complicated and kind of scary is once you've created this, well, that means that no matter what you do, you have some kind of delay between one MOSFET and the next. Um, and that is going to be mostly what's going to set how fast you can clock things. Yeah, you can increase your voltage supply to make it go up and down faster, which is overclocking. But but there's problems. You can't go too high, or else you're going to burn out the chip. Now, what's another interesting thing is this insulator inside of your chip is actually really, really, really thin. It is actually like, because it's so thin, your capacitance, which is area over the like the thickness of your insulator times, of course, your dielectric constant, which is your capacitance, that actually creates a really good capacitor. So what this capacitor really is trying to be, I'm pretty sure, is actually trying to talk about this capacitor that you make through this super thin insulator right above the silicon, which is called the metal oxide semiconductor capacitor, or MOSCAP. But again, that's not really super accurate anymore. It's a bit of a misnomer because the actual metal is actually polysilicon. So so that's what a capacitor on an integrated circuit actually is. And there's some really strange specific rules that you have to be careful of when you talk about this type of capacitor, because the silicon beneath it is not ideal. It's doped with either P or N. If it's not doped at all, it's not going to conduct electricity, which is why these capacitors start to get really weird and finicky. And also because one side of the capacitor is on the silicon and the other side of the capacitor is connected through an interconnect to metal or whatever. Another problem is your parasitic capacitances are different between the top of the capacitor and the bottom of the capacitor. So little things like this means that the capacitor isn't ideal, and you have to be really careful with how you design things around that. This game definitely takes a lot of liberty when it comes to how it portrays capacitors, and that is probably one of my biggest complaints. But then again, this game is very much, number one, of course, it's a game, and it's also very much concerned with digital. And when it comes to digital, these things are much less important. So, can I forgive it? Yeah, that's fine. Honestly, what do I think about this overall? It's very fun. The problem is, I really wish the play space was a lot bigger. This is a very, very small play space, and I especially towards the end of this, I'm very much feeling this limitation. It's reminiscent of the reactor space problem that you have in Space Chem, but even the reactor space was 8x10. This is 6x5. This is and your transistors are pretty honkin' huge here. So yeah, you could make the argument that if you make the play space too large, then what ends up happening is your routing gets really easy. But that's how things are in the real world. Your routing fabric, like your metal 1 and your metal 2 and etc., it gets a lot easier in the real world because you have so many metal layers to go and route and everything. So Eknerwala says that they also feel the entire difficulty is the play space size and doesn't know if that's a fun source of difficulty. Honestly, I personally would think that building more and more complicated circuits would be more fun. I would like to, take this and extrapolate it to more and more complicated things. Things that are more than just 6, like input outputs slash, that kind of thing. And things that are more complicated. one of the funny things is, yeah, here, I'll go and see if there's a, I wonder if there's I guess there's not a sandbox, but okay, this one I don't even have. Okay, so let's go over here to this one and let's just talk about some other thing. This circuit right here. This circuit right here is a perfectly valid circuit. Yes, it is. If you talk about digital circuits, yes, this is kind of weird because it shouldn't work. But it is, what this really is let's see here. Gate goes to here, and so your VG is going to be, your VG minus your VS is there. So this is a VGS, yeah. So what this is essentially the ground side equivalent of this circuit right here. These two are almost the same. The only difference is that this works, and the bottom one gets really angry at you if you try to make this in this game. But really, these should both work, which is one of my gripes, because there's really no reason that, because what will happen is, in the real world, this is going to charge up this side, that's going to pull this up, and this is going to gradually reduce the amount of, current going into this node until it reaches some equilibrium. And it's kind of like a diode in that aspect. The only difference is, in this game, the game likes to treat positive power and negative power differently. That's also something that I have slightly. It's probably actually invalid digital circuitry. Well, no. So this circuit right here, this top circuit, do you see any problems with this circuit at all? So the truth is, this circuit up here doesn't have any problems, because you've got this gate here, you've got this source, or it's actually the drain, because the source is on this end on a NMOS. So what happens is, yeah, so right, there's this weird implicit pull down behavior in this game that is really strange. But the idea is, this circuit up here, the output of this circuit, is that this tries to output high. It gets pulled up high until it's about 0.7 volts from the power rail. When it gets to 0.7 volts of the power rail, suddenly the amount of current that this circuit is able to supply drops dramatically. And the reason why is because you need at least 0.7 volts across these two nodes for this to actually turn on and conduct. Over here, well, this is really the same thing, except this is about pulling it down. So the idea is, even if you have a tiny little bit of load over here, and it tries to pull it all the way up to the power source, it's going to stop at about 0.7 volts below the power source. And that's kind of a problem if you're using a lot of these. So, but this game doesn't care about that. The other thing is, when you Right. It really depends on how much load you're putting on here. If you're putting on a lot of load, it'll stop around 0.7 because if it tries to dip below that, this will easily supply a lot more current. If you make the load very light, then this will try to pull it even closer and closer and closer to the power source. It won't really ever get to the power source unless there's absolutely like no load here. Yeah. And over here, if I connect this to ground, because this game doesn't really have a ground for some reason, then it is really just a diode. Because my there's like a 0.7 volt drop over here, and it'll constantly be sourcing or sinking current. Of course, yeah. So yeah, again, it's one of those. It doesn't. It takes its liberties very much so, because one of the things that I was able to do in this game that you isn't 0.7 bad for digital circuitry though. Depends. It depends. It all depends on how your transistors are characterized, because that's not a hard and fast rule. The top circuit is also invalid. The top circuit is actually very much valid. Yeah, so this is a diode. One of the things that you really shouldn't be able to do is this. So this kind of thing here, even if you add more capacitors or whatever, that just does not ever happen in real life. I probably don't need to elaborate on why that doesn't work in real life, but the TLDR is, in real life, what this would do is this would charge this up. This part of the circuit will charge slowly because there's a big capacitance on it, and then it'll go up and up and up, and then it'll reduce it'll increase the voltage on here, which will reduce the current going into here, and it'll kind of just exponentially, the voltage will go up slowly, and then it'll level off essentially. And it'll very, very slowly get up to this power source because it's not being loaded down by anything. Yeah, it does not oscillate. This kind of circuit does not oscillate in real life. That would be very, very weird. But then again, I do feel like it's a little bit unfair for me to judge the game to this depth of detail. Mostly just because, like, it's... A lot of these things are analog, and if you want to, start talking about analog things, then the amount of complexity and the amount of previous knowledge that you need to even do something like this gets ridiculously hard. So it's really not fair to judge this from an analog lens. But yes, there's definitely some strangeness with how this game likes to treat its capacitors. So I don't remember if Constructor is like the same, but I do know that one of the things that I really wish this game kind of had instead is that instead of all the capacitors discharging instantaneously, it would be more like a delay line. So it would, do this, and then when the thing turns off, it will also like kind of turn off in sequence. I think that would be really cool. Yeah, the capacitor's turning off instantly. Whatever. Yeah. Other things, I really wish there were diodes. The one thing that this game is really missing is that there are diodes. I cannot make a P to N connection like that. And that really peeves me because diodes are so important, especially when if you're this limited. Um, yeah, I really wish there were diodes. Oh well. To the zeroth order, capacitors are actually two separate pieces of metal. Yes. So the way that this game likes to generalize capacitors is says, okay, well, yeah, here's a capacitance, but what you would really be doing is you would actually have interconnects or vias underneath that. You would put a via underneath these, so that it would be actually be connected to the polysilicon, which is right above the actual silicon, right? And it's actually between the polysilicon and the silicon itself where you have this huge capacitance. So if you want to increase capacitance, what you would actually be doing, is you would put a contact from here or a via from the metal to this polysilicon layer slash like this conductive layer right above the insulator, which is right above the actual base silicon. So that's what you would actually be doing to create this kind of capacitance. But yes, overall, my thoughts are it's a fun game, but I definitely feel very limited in the amount of stuff that I can do. I would love to do. I would love for there to be like a second design browser, um, with like way more complicated things, like maybe like a second window, um, with a much more complicated circuits and a much larger like expanded layout slash ignition sequencer thing. That would be really cool. Yeah, so I would say what I would want in this game is I want there to be diodes, and I want there to be a bigger play area. Those are my two biggest grievances. Yeah. So yes, you can make diodes in game, but they're like that. Like this is a diode connected MOSFET, or no, it needs to be the it's supposed to be NPN and the P type this way. Yeah, this is a diode. If this is high, it'll conduct this way. If this is low, it doesn't conduct that way. Yeah, it doesn't conduct in reverse. And you can simplify this to just like N here, P, and you just do that. I also wish that there were kind of like corner transistors. That would be very nice, but I understand that. Whatever. Yeah. Anyway, thank you all for coming to my rambling, my rant on this game. Do I like it? Yes. It is very fun, but then again, like, I can't ask too much when it comes to the really small, intricate parts of this thing, because at that point, you're just really, like, coding like a circuit simulator, right? And like we're trying to make games here. We're not trying to make circuit simulators. Yeah, but yeah, if this kind of thing interests you, definitely consider doing digital design. Design verification is also something that's very high in demand. Analog design, of course. Yeah, these are all fields of technical engineering where there's a lot of demand for it, and especially analog. Um, the analog field is actually ever since people started growing up in the age of like digital computers, analog really has like fallen behind and has fallen to the wayside. Even though it's at the end of the day, you need analog in everything. Everything that's power, everything that's supplying power to any circuit, that is all done in analog. There is no digital there. and there's still the area of analog computation has recently gotten there's been recently there's been an uptick in it, but it's a lot of it is just like people get interested in coding, and they're like, oh, okay, well, I can just do digital design. And yeah, digital design is nice because things tend to work much easier, and in analog you don't have that same kind of assurance. Most analog chips, I believe like 20 or 30 years ago, if you wanted to make an analog chip, generally you had to go and test it out, like send it off to the fab 2, 3, or 4 times before you've done enough revisions to which it actually works. In digital, that number is much, much closer to one, like 1 or 2, and you just do it. You try it once or twice, and you've got a working chip. Analog, yeah, it generally takes a lot more because there's just so many complexities to it and magic. Yes, the design tools, the CAD tools that we use nowadays are much more powerful, and they allow us to catch a lot more things before it gets sent off to the fab. So the number of design revisions that we have to make before we have to the amount of design revisions before we make a working chip is now closer to 2. It's still it's still more than the digital side, but it is definitely still like, yeah, and yeah, you just have to know a lot of these complexities and all of these things. But yeah, let me take a read. Yeah, to zeroth order capacitors are actually 2 separate pieces of metal. Yes. Rami says, thanks for the stream. I'm glad that you enjoyed it. And Blazing says, my current assumption is that these capacitors could be treated as dielectric material that, though through its mere presence alone, speeds down the speed of electricity, which might justify why they don't hold charge. Yeah, so this brings back the idea of transmission lines. So if you have the right material, you could slow down the speed of electricity, but you're really messing around with some really strange and interesting materials at that point, because you're talking about the electromagnetic field propagating not through the medium of a vacuum or air, but some kind of dielectric that will slow it down, a very, very high dielectric constant that will slow down the speed of propagation. The problem is, dielectric constants can be high, but they're not high enough to slow down the speed of light to the point where a clock cycle versus a single grid square. Yeah, unfortunately, that's kind of not that doesn't really happen. And even if you did, and this electricity, propagates through this, say, a line of capacitors at this very slow speed. The problem is when you turn off the energy at the very source, that information there still needs to propagate through all of these capacitors as well. So even if you cut power to all of that, the capacitors should go off one by one by one. It would definitely not just instantly all turn off at the same time. Yeah. So yeah, that's definitely something that's very strange, and unrealistic. Would I recommend that for a game change? No, because if you do that, then well, number one, I believe it would actually make this a lot more stable. Like, you don't have to worry as much about these strange, like, sub-cycle oddities. But the thing is, this game is kind of designed around the capacitors being this way, and a lot of the problems that that are released in Last Call BBS, all of these are, and all of these design problems, they were designed with the intent that the capacitors work in this way. So I think it's a bit too much of an ask to change capacitors to work slightly differently. So I think that's fine. But yes, I do wish that for if there are more designs in the future, I do wish that we have a larger playing space, and I do wish that we have diodes. That would be those are my two um, my two the two highest that are on my wish list. I wish there were diodes, and I wish we had a larger playing space. But yes, overall, it's a good game. It is rather tight on the amount of stuff that you can do, but yeah, bigger playing space, diodes, and a sandbox. There's no sandbox, which is really strange. I wish there was a sandbox. All right, I'm gonna call that a day. I've been streaming for wow 5 hours. Got through ChipWizard Professional in one sitting. So thank you all for coming, and I think next week I'll probably end up going back to playing Diablo 2. And there's also a Space Cam stream coming up this Thursday because I need to do week 5 again. So yeah. Alright, thank you everyone, and I will be hopping off now. Bye-bye.